So our goal now is to define a function f that takes a sentence, for example, the dog barks, in conjunction with a tag sequence, for example, dnv, and returns some feature vector. And so to do this, we're actually going to use a lot of the machinery that we developed for log linear taggers a little earlier in this course. We'll reuse directly the concepts we saw there. So a first critical concept was the idea of a history, which basically captures all of the context which is in play when we're making a tagging decision. So as we saw a few lectures ago in log linear models, a history is a for tuple consisting of a pair of tags t minus 2 and t minus 1. For example, if we're tagging the word base, in this case we would have t minus 2, t minus 1 is equal to determiner followed by an adjective, these two tags. We have the entire sentence. So in this case we have this entire sentence here as the second element of this tuple. And then we have to be slightly careful to specify the position in the sentence that's being tagged. In this case we have the 1, 2, 3, 4, 5, 6th word being tagged. This is word number 6. And so that's the fourth element of this history. So when we consider what possible tag we should choose in this particular location, we're basically going to use the history to encapsulate all of the information which goes into that decision. Now, recall that we've made the assumption that the history only looks at the previous two tags. In the case of log linear models, that was motivated by concerns about efficiency. That allowed us to use the Viterbi algorithm in the decoding problem for log linear taggers. And we're going to use this assumption again, and we'll see how, again, in global linear models, it also allows us to apply dynamic programming algorithms. So now to go further with this, again, this is just actually reusing completely the technology we saw from log linear taggers. We will define what I'll call local features. So remember, a global feature vector looks at an entire xy pair where x is, for example, a sentence, say the dog barks, and y is some tag sequence. So these feature vectors are global in that they look at an entire tag sequence. Now I'm going to define local features which just look at a history tag pair. And so they're going to look at a very small window. In fact, they're going to look at a sequence of 3 tags, 3 consecutive tags, because a history contains 2 previous tags, and then we look at this third tag. So I'll use the notation little g for these local features. So g sub s is a function that takes a history tag pair as input and returns some value as its output. Very often in natural language, these local features are binary features or indicator functions, which ask particular questions about the history in conjunction with the tag being proposed. So here are some examples we saw actually in the log linear tagging lecture. G100, for example, might be a feature which is 1 if the current word wi being tagged is the word base and the tag being proposed is vv. G101 might be a function which is 1 if the current word ends in ing and the tag being proposed is vvg. We can also have contextual features which look at the tag being proposed and these previous 2 tags in the history. So here's a feature which is 1 if the trigram of tags, the previous 2 and the tag being proposed, are the sequence determiner, adjective, verb, and so on. And as we saw in the lecture on log linear models, one great thing about these kind of feature vector definitions is that you can essentially ask any question about the history in conjunction with the tag being proposed that might be useful in disambiguating the tag at the current position. So now, if we think about an entire xy pair, okay, so I'm just again emphasizing that our goal is to define a feature vector representation of an entire input x with an entire output y. So I sort of have x together with y here, I have a sentence with a particular tag sequence. If there are n words in that sentence, then there are n history tag pairs within that XY pair. So this particular sentence has 1, 2, 3, 4, 5, 6 words. For convenience, I'll just number them. And we have 6 history tag pairs for this particular example. So the first history tag pair has the tagging decision NNP, because that's the tag for the very first word, and the history has the previous 2 tags as these start symbols, these star symbols. We have the entire sentence, we have position 1. The second history tag pair has RB, because that's the tag of the second word, the entire sentence, position 2, and the previous 2 tags are star and then NNP. The third tagging decision is VB, because that's the identity of this third tag here, and the previous 2 tags are NNP and RB. And so on and so on. You see we have determiner at the 4th position, adjective at the 5th position, base at the 6th position, and in each of these cases we have a history where the sentence of course is staying constant, but we have the position being indicated of the particular tag, and we also have the previous 2 tags at each of these positions, which obviously is changed as we modify this index, this position of the sentence. Now, each of these decisions, each of these positions, is going to have a local feature vector, G. So I'm going to have a feature vector for this first decision, which consists of the history in conjunction with the tag NNP, where the history is this particular history here. This feature vector has G of the second history in conjunction with RB, and so on. And so there are going to be 6 local feature vectors corresponding to the 6 different history tag pairs in this particular tag sentence. So let me now show how we can leverage these local feature vectors in defining a global feature vector that maps an entire tag sequence in conjunction with a sentence to a feature vector.